Exploring the idea of pi, the ratio of the circumference of a circle to its diameter with frequency wave theory presents an intriguing, though speculative, framework. The endless, non-repeating decimal expansion of pi has fascinated mathematicians, scientists, and philosophers alike. When we consider this from a frequency wave perspective, we can contemplate several hypothetical and creative approaches. Non-repeating frequencies in pi, aperiodic waveforms. The sequence of digits in pi could be considered analogous to an aperiodic waveform, which never repeats exactly the same sequence or cycle. In frequency wave theory, such a waveform would not have a single fundamental frequency, but a complex spectrum of many frequencies that never align in a simple repeating pattern. This could metaphorically reflect the mathematical property of pi being transcendental and not solvable by any finite algebraic expression. Fourier analysis of digits. If we consider applying Fourier analysis to the sequence of digits in pi, where each digit, 09, is represented as a distinct signal or wave, the resulting Fourier transform would hypothetically display a spectrum representing the distribution of energy across different frequency components. The non-repeating infinite nature of pi might then be visualized as a Fourier spectrum that shows no predominant frequencies or periodicity, symbolizing the infinite complexity and unpredictability of pi. Quantum interpretations of pi. In a highly theoretical sense, one might imagine the digits of pi as states in a quantum system where each digit represents a different quantum state. The progression through these digits could be akin to a quantum system evolving over time without ever settling into a repeating pattern. This non-repetitive behavior could be linked to chaotic systems in quantum mechanics, where initial conditions can profoundly influence long-term behavior, yet remain bounded within deterministic rules. Modeling natural phenomena, pi's properties might be used to model phenomena that are circular or cyclical, yet have layers of complexity, such as wave patterns in fluids, the distribution of stars in a galaxy, or the properties of certain materials at the atomic level. The idea here is that the frequency components derived from modeling these phenomena could share some analogous mathematical characteristics with the distribution of digits in pi. Encoding information in waveforms. On a speculative note, if we consider the possibility of encoding information in the sequence of digits of pi, using a system where these digits modify the amplitude, phase, or frequency of waves, we could create a complex waveform that carries encoded data in a pattern as infinite as pi itself. Philosophical and metaphysical considerations. Pi as a model for understanding the universe could also be viewed through the lens of frequency wave theory as an example of the underlying order and yet apparent randomness present in the universe. Just as pi continues indefinitely without repetition, so might the universe exhibit patterns at various scales that are non-repeating but bound by physical laws. In conclusion, while these explorations of pi through frequency wave theory are imaginative and not based on current scientific consensus, they offer a way to think about the connections between mathematical constants, wave phenomena, and the broader universe. These ideas bridge abstract mathematical theory with physical phenomena, illustrating how deep and sometimes mysterious the links between.